Greetings to everyone, and now we're going to tackle the lesson about buffers. But before we head on to our lesson, we have two learning objectives. The first one is to describe the composition and function of acid-base buffers, and second is to calculate the pH of a buffer before and after the addition of added acid or base. Now, what is a buffer? A buffer is a solution that resists sudden changes in pH when small amounts of acid or base are added. So basically, a buffer resists pH in a specific range. And if some of you are asking, what is a pH? A pH tells us if something is acidic, basic, or neutral. A pH level has 0 to 14 range, wherein 7 below is acidic, 7, like exactly 7, is neutral, and 7 above is basic. It measures how acidic or basic a solution is, and pH is also known as potential of hydrogen. Now, how does a buffer solution work? In the next slide, we'll present a video to explain how a buffer solutions work, from the complete guide to everything.
In this video, I'm going to give you a nice simple explanation of how buffer solutions work. So let's start with a beaker. And this beaker contains a solution, and this solution has got some universal indicator in it, and it has a pH of around about 7. It's neutral. We take some acid, as represented by some H plus particles. That's our particle for an acid. We add those H plus, which represents adding an acid, and unsurprisingly, the solution would turn a kind of red color. So universal indicator is indicating that we now have an acidic solution. That makes sense. We start with our same solution with some universal indicator in it, turned green. We take some alkali, which is our OH minus. We add that, and unsurprisingly, the color of the universal indicator would change, and we would end up seeing that we have an alkaline solution. However, if we had a solution with a buffer in, things are going to be very different, and it's going to behave a little bit strangely. If we took some acid, and I mean a little bit of acid, not an enormous amount of acid, just a little bit of acid, we add a little bit of acid, and that acid goes into the solution, and nothing happens. We could take some alkali, add some alkali to the solution, and again, nothing happens. This is the magic of buffering. We've added an acid, the pH hasn't really changed. We added an alkali, the pH hasn't really changed. That is the point of a buffer. A buffer can maintain a solution at roughly the same pH and resist the action of acids or alkalis that are added, but it only works up to a point. If you added an enormous amount of acid or an enormous amount of alkali, it wouldn't keep working. And the question now is, what is going on here? How is it possible that you can add acid or you can add alkali and not be changing the pH? That is very strange. And it actually turns out there is two things going on here. One of the things deals with the acid and one of the things deals with the alkali. So you actually have two main ingredients in a buffer solution, and we'll look at what each one is and how each one works. So we have our solution here. One of the two components of our buffer solution is going to be a thing called HA. And the question is, what is HA? What is this key component? And it turns out that HA is simply the name of a weak acid. So any weak acid can be represented by HA, where H is obviously hydrogen, which is a key part of an acid, because you need to have H plus particles, and A simply represents whatever else you need to add to H to complete your weak acid. So it could be an acid like ethanoic acid, or it could be a wide range of other weak acids, say benzoic. So HA is just how we're going to represent any weak acid, and that is one of the two ingredients of a buffer solution. So we have an equilibrium going on here. So we have a weak acid will dissociate, and it will produce H plus, and it will produce A minus. So this is splitting up. A minus is what we call a conjugate base. The equilibrium, however, isn't a fair equilibrium. It's not half and half. The equilibrium is very, very much towards the left-hand side because this is a weak acid. Weak acids partially dissociate. So most of the HA is going to be undissociated, and you're only going to get very, very few H plus and A minus. The vast majority is going to stay as HA. So that's why adding the weak acid isn't going to immediately turn your buffer solution into, going completely red and being an acid in terms of pH. So let's look at how this actually works in practice. So we have our solution there that's buffered, and we know that one of the components of a buffer solution is our weak acid HA. So let's think about how would HA react if it was exposed to some alkali particles, so some OH. Well, what happens is your weak acid reacts with your OH and produces water and your conjugate base A minus. Now, this is, of course, alkaline because OH minus is your alkali particle, but water and your conjugate base, this is overall going to be neutral. This isn't going to be alkaline. So what happens when you add your base, which is your OH minus or your alkali, you add that there, it's going to react with your HA, which is your weak acid. These two react, and of course you get this produced, so they react together, and you end up with this. This isn't going to change the pH of your solution very much, and you're going to end up with a pH that's virtually unchanged. Of course, if you added an enormous amount, an absolutely enormous amount of OH minus, it would absolutely overwhelm the HA. You would run out of HA and it would no longer be buffered. So buffers only work up to a point. This is how you deal with OH minus or your alkali. What if we added an acid? Well, this isn't going to work. We're going to need to add another ingredient. So we've got some acid particles there. We want to add these. And obviously, there has to be some sort of reaction that gets rid of these. Now, we know there's this equilibrium here, which we've seen earlier. This A minus could, of course, react with this H plus. But remember, this is a weak acid, so we're not going to get very many of these. These are going to be gone very, very quickly. So simply having HA as the only ingredient in a buffer isn't going to work because the equilibrium's far too far to this side, far too few of these. So the trick is to add a soluble salt of HA. So for example, we could have NaA. So whatever A is, we could have sodium of that. Now, we have this reaction here, which is NaA fully dissociates into Na plus and A minus. Na of A is going to be a strong base, so that's why I've showed it with this arrow, showing that it fully dissociates. Because it fully dissociates, we're going to get loads of A minus. There's going to be loads of A minus floating around. So we've actually got loads of A minus. This is minus, this is plus. Unsurprisingly, there's going to be a reaction between those. So those two react and you end up making your HA again, which is one of your ingredients of your buffer solution. And the HA is, of course, a weak acid, so it's going to only partially dissociate, so it isn't going to have very much effect on the pH. It's going to have a little effect because you're going to have some H plus produced, but it's not going to be a very big deal. So a buffer can maintain the pH between very narrow values as long as you don't add enormous amounts. So you've seen our two components of a buffer solution are your weak acid and the salt of that weak acid. So you now know how a buffer works. I hope this video was really helpful to you and it's finally making some sense. If this video did help you, please comment below and let other people know that this video is helpful to them. And if you like it and subscribe, that also encourages me to make more videos and suggests that this is actually helpful. And finally, thank you very much for watching.
Now that we've watched the video on what happens to the content of a solution when buffer is used to keep pH constant, let's move on to the next slide. Henderson-Hasselbalch equation. This allows us to calculate the pH level of a buffer solution. Now the word Henderson-Hasselbalch came from the name of two scientists named Lawrence J. Henderson and Carl Albert Hasselbalch. Lawrence J. Henderson developed an equation in 1908 to describe a buffer system. So the solution that we can see just near the description of Lawrence J. is the equation that he had developed in his time. Henderson studied bicarbonate buffer system, which helps keep blood pH nearly constant even when acids or bases are added. Now in the solution, it it is expressed that the relationship between the concentration of an acid and its conjugate base in maintaining an equilibrium. This is also the ratio of base to acid, which determines the hydrogen ion concentration in a solution. Now, in Karl Albert Hasselbalch's time in 1916, he modified the equation into its modern logarithmic form, which is widely used today. The solution of Karl Albert Hasselbalch will be, and Lawrence J. Henderson will be shown later on in this lesson. There are two types of buffer. The first one is acidic buffer and basic buffer. Now, the acidic buffer is made from a weak acid and its salt with a strong base. It keeps pH on the acidic side below 7. An example of this is a solution of acetic acid and sodium acetate produces a buffer solution with a pH around 4 and 6. And for the basic buffer, it is made from a weak base and salt with a strong acid. It keeps pH on the basic side above 7. An example of this is a solution of ammonia and ammonium produces a buffer solution with a pH level around 9 to 11. And now for the examples. A solution of acetic acid and sodium acetate is an example of a buffer that consists of a weak acid and its salt. Now if you look back to the other slides that we have discussed earlier, this is a type of buffer called acidic buffer. And when the weak acid is added, the conjugate base part of the buffer, which is the salt, reacts with the extra H plus ions and removes them, and it prevents the large drop in the pH level. And now for the second one, a solution of ammonia and ammonium chloride is an example of a buffer that consists of a weak base and its salt. Now in this example, when the base is added, the weak acid part donates H plus ions to neutralize the OH minus, preventing a large rise in pH. So basically, the other pair of it neutralizes the other either base or acid that is added into the solution. Now, just like what I've discussed earlier, when the acid is added into the solution, the base part neutralizes it. And when the base is added into the solution, the acid part neutralizes it. So when we add the acid, it causes a drop in the pH level. So that's why the base part is there to neutralize it. And when we add the base, it causes a large rise in the pH level. And the reason why the acid part is also there is to neutralize the rise in pH. And now onto the buffer capacity. Buffer capacity means how much acid or base a buffer can handle before the pH finally changes a lot. So when it's a small buffer, it can only handle a little acid or base, and when it's a strong buffer, it can handle more before breaking down. And whenever it is a small buffer, it only neutralizes an amount of acid or base before the pH changes. And when it is the strong buffer contains higher concentration, so you can add more acid or base to keep the pH almost constant.
At dito naman po tayo sa limits of buffer po. So yung buffer po natin ay limitado lang po lamang. Sa nakikita niyo po dito, buffers don't work forever. If you add too much acid or base, the buffer gets full and the pH will change. So kung magdagdag po tayo ng acid or base, too much acid or base, yung buffer solution po natin ay magbabago. Kung sa atin pa, kung magdagdag po tayo ng too much acid or base sa buffer po natin, yung buffer po ay mabubusog. At yun, magbabago po yung pH ng buffer. So the importance of buffer. In the human body, our blood has a buffer system, the bicarbonate buffer, that keeps pH around 7.4. If not, even small changes could be dangerous. So nakita niyo po dito na 7 na yung dugo po natin ay may pH na around 7.4. Di ba yung neutral po ay around 7. So yun, nakikita po natin na balanse po talaga yung dugo po natin. So yung pangalawa po ay in food. The buffers keep flavors stable. The third is in shampoos and soaps. Buffers prevent them from being too harsh on skin. At yung panghuli po ay in experiments and industries. So yung buffers keep reactions working properly. Yun. So may simpleng analogy po yung buffer natin. Ang buffer po ay parang bodyguard ng pH po. Small attacks come in, but the bodyguard blocks them so pH doesn't change much. But if a whole army comes, the bodyguard gets overwhelmed. So yun po, yung buffer po natin ay parang bodyguard sa pH po natin. Kung magdagdag po tayo ng only small amounts of acid or base sa buffer po natin, yung pH po ay hindi magbabago. So bale yung buffer po natin ay i-block po yung mga acid or base para hindi magbago yung pH natin. But if we add too much acid or base po sa ating buffer, magbabago po yung pH ng buffer natin. Kasi limitado lang po yung buffer po natin. It will only have the capacity of small amounts of acid or base. But if it is too much po, then magbabago po yung pH ng buffer natin. So dito naman po tayo kung paano po natin i-calculate yung pH ng buffer natin. Both before and after we add acid or base. So yung formula po na ginagamit natin sa pag-solve or sa pag-calculate ng pH ng buffer po natin ay the Henderson-Hazelbach equation. Yung nasa screen po natin, makita nyo na yun naman po dito. Ito. So, isang halimbawa po. Suppose po we have a buffer made of acetic acid and sodium acetate. And sila po dalawa ay may same concentration. 0.1 mole. At yung pKa po natin of acetic acid, which is our acid, is 4.8. So, bale from the given po, i-substitute po natin yung nakuha pa natin sa given at i-substitute sa ating equation. So, ito po yung mukha po ng ating Then, pag i-calculate po nyo ito sa calculator, ang makukuha nyo po ay 4.8. So, wait. Yun. That means yung buffer po natin, before we added anything, is 4.8. Dito naman po tayo, dito naman po tayo sa pag-add ng acid. So, when we add acid, the acetate ion in the buffer reacts with the extra hydrogen ions from our HCl, which is our acid. It will form a more acetic acid, and which changes the balance kunti lang. Dito naman, so let's say po na yung base po natin ay magiging 0.1 to 0.009. At yung acid po naman ay mag-change from 0.1 to 0.11. At nakuha po natin ang sagot niyan ay 4.71. So before we added the acid, yung sagot po natin, yung pH po natin ay 4.8. After adding acid, it only dropped a little to 4.71. That shows us how a buffer resists big pH changes, even when acid is added. So the same thing din po mag-happen kung base po yung ating gagamitin. The weak acid in the buffer reacts with the base, and the pH only increases slightly. So yun lang po. Kung gagamitin po yung equation na Henderson-Hazelback equation, we can calculate and prove that buffers really work to keep the pH almost constant. So yun lang po. Yun lang po sa problem solving po natin. So ito po, key points po ng ating lesson ngayon. Buffer resists sudden pH change. May two types po na buffer. Acidic buffer, which yung pH po ay less than 7. At basic buffer, na yung pH po ay greater than 7. Buffer is made of weak acid plus salt or weak base plus salt. So yun. A buffer works by neutralizing added acid or base. So yung buffer capacity po is how much it can handle before breaking or how much it can handle before the pH changes. Yun po. So yung buffer po ay important in blood, food, products, and labs. So yun lang po yung video po natin na buffer po. Sana po may natutunan po kayo sa aming lesson ngayong umaga o gabi. So yung PPT po nito ay nasa description lang po lamang ng video po natin. So yun lang po. Maraming salamat po sa pakikinig.